Welcome back to GSO Physics, Lesson 1-2. Today we also want to look at another set of physical quantities titled Dimensional and Dimensionless Quantities. Introduction. Having introduced you to the first kind of physical quantities in physics, that is the fundamental, basic, and the derived quantities, in this lesson, you will learn about the second kind of another set of physical quantities known as the dimensional and dimensionless physical quantities. What is a dimensional quantity, or what is a dimensionless quantity? Examine this equation. 4 plus 5 is equal to 9. You will observe that this is a balanced equation because the values on both sides of the equation are balanced, or they are the same. In physics, equations are usually used to equate physical quantities that have magnitude, that is size, dimensions, and units. All the three must balance for the equation to make sense. I will repeat. In physics, equations are usually used to equate physical quantities that have magnitude, that is size, dimensions, and units. All the three must balance for the equation to make sense. What then are dimensional and dimensionless quantities? Dimensional quantities are physical quantities whose measurements depend on the magnitude or the fundamental units, and which are different in different unit systems. A dimension is the type of quantity which is independent of its units and values. Examine the following physical quantities: 100 centimeters, 1.0 meter, 5 kilometers, and 5 light years. They all have the dimension of physical quantity called length, but expressed in different units. The figures or numbers show their magnitudes or sizes, which are dimensionless. Again, consider the following equations. 3 kilograms plus 5 kilograms is equal to 8 meters. Equation 1. 3 meters plus 5 meters is equal to 8 centimeters. Equation 2. Recognize that in equation 1, the values balance, but the units are different on both sides of the equation. In equation 2, the values balance, but the units are not the same on both sides, but are of the same dimension of length. Equation 1 is meaningless in terms of the dimensions of mass on the right side and length on the left side. Equation 2 is correct in terms of dimensions because the two sides have the same dimension of length, but the units are inconsistent. Note that the equations whose dimensions and units balance are said to be homogeneous. However, homogeneity does not guarantee that the equation is correct. For example, F is equal to ma, that is, force is equal to twice mass times acceleration. It is homogeneous, but not correct. And you'll notice that the correct expression should be F is equal to ma and not F is equal to 2ma. The use of dimensions is a way of showing how a physical quantity is related to the fundamental, that is, basic quantities, which are mass, length, and time. Why do we study dimensions of physical quantities? You may ask. They are used to check the given equation or formula is correct. Suggest the form of equation should take. That is, they suggest the form an equation should take. The dimensions of a physical quantity are expressions which show how the quantities such as mass, length, and time from which it is derived. For example, m represents the dimension of mass, L represents the dimension of length, while the capital T represents the dimension of time. What are the dimensions of area, volume, density, speed, and acceleration? We use the square brackets to mean the dimensions of what is contained in the brackets. For example, when we say area, square bracket A, is equal to L squared, the unit is m squared. Volume, the dimension of volume is written in form of the square brackets with V inside, which is equal to L cubed. That is, the unit is m cubed. Density, rho, is equal to mass per volume, which is equal to ml, L minus 3, and the unit is kilogram per meter cubed. Speed, the square bracket with small letter v inside, defines the distance per second, which is L t minus 1, and the unit of which is meter per second. Acceleration is square bracket A in the middle, and that gives me the displacement per second squared, which is L t minus 2, the unit of which is L meter per second squared. Further exercises. Determine the dimensions of the following physical quantities: force, pressure, work done, kinetic energy, potential energy, and power. Part 2. Dimensionless quantities. Dimensionless quantities do not depend on the system of units, so they are dimensionless. The following are dimensionless quantities. 1. Whole numbers as well as fractions have no dimension. Angles and their trigonometrical ratios are also dimensionless. Physical quantities obtained through ratios such as relative density are also dimensionless. The efficiency of a machine is also dimensionless. All pure numbers, logarithms, and indices are dimensionless. Part 3. The application of dimensions. Dimensions are used in checking physical equations or to predict the relationship between physical quantities. To be sure that the dimensions on each side of the equation are the same, correct, and valid. The process of doing this is described as dimensional analysis, which is very useful in physics and engineering. It can also be used to check the correctness of certain equations. How can you validate the idea that the period t of a simple pendulum is independent of the mass of the pendulum bulb? Further exercises. When two bodies, M1 and M2, are separated by a distance r, Newton's universal gravitational law states that the force F between the two bodies is expressed as F is equal to what? Big letter G, M1, M2 over R squared, where the big letter G is the universal gravitational constant. Can you determine the dimensions of G? From the second law of motion, expressed as F is equal to m delta v over delta t, the impulse of a force is expressed as F delta t, which is m delta v. That is, the impulse of a force, F delta t, is the same as the change in momentum, m delta v. Determine the units of the impulse and the units of the change in momentum. It will be observed that the units are not the same. What are the dimensions of the impulse and the change in momentum? You will observe that the dimensions are the same. Summary. Dimensional quantities are the physical quantities that can be expressed in terms of the dimensions of mass, m, of length, L, and of time, T. The quantity mass is represented by big letter M as the dimension of mass. The quantity length is represented by big letter L as the dimension of length. And the quantity time is represented by big letter T as the dimension of time. Any physical quantity that is expressed with mass, length, and time and can be computed in terms of m, L, and T, the dimensions of mass, length, and time, respectively, are to be regarded as dimensional quantities. Dimensionless physical quantities are those physical quantities that do not depend on the system of units. Thank you for listening.